Well, hi, my name is Alex Tseng, and this is my 5-minute YC fellowship application video. I'll start by saying that for the summer, I'm really interested in understanding how we can use AI and optimization and improvements in sort of computational abilities in order to create an electric grid that's more efficient and resilient, more intelligent, basically a smart grid. It's something that we've talked about in academic circles for a long time, and I think that it'd be really cool to spend a summer actually trying to do something like that. And so in that vein, I'm going to actually be demoing a couple of different projects. The point being, there are multiple different projects that, one, indicate my technical abilities in sort of this specific field, but two, maybe they'll give an indication of what I would be interested in continuing on for the summer and sort of the product I'd like to build. So the first thing that we're looking at is called a capacity expansion model. This is written in Julia, and basically it is one large convex optimization model that takes a bunch of variables, which are generators, technologies available for electric generation, transmission lines, energy storage, etc. And it runs a convex optimization model where the decision variables are, one, what to invest in, which generators to invest in, transmission lines, etc., and then two, how to operate all of that. The objective function is the cost of the whole system, and the constraints are essentially the reality of electric grid. I'm creating a modeling situation where you're actually modeling what the grid would look like, and then two constraints to meet the electric demand of a population. And so what this convex optimization is doing is it's actually modeling the optimal way to expand our grid, in this case for the western half of the United States, the WEC, in the year 2035. And so it tells us the least cost way to meet all electric demand. This particular code is actually really interesting because it iterates over several different policy options, constraints that model different decarbonization policies. And so it actually tells policymakers as well which decarbonization policies are the most effective at economically reducing CO2 reductions. Obviously, the whole thing is a little bit more nuanced than that, as you can see here, but it's a really cool example of how we can use sort of advanced optimization, Bender's decomposition, or spatial decomposition, and simply just better computers to better plan grids. And it's certainly a good indication of my technical ability and sort of interest in that. Planning grids is obviously one really important facet of improving grid modeling, but the other thing is the real-time operation of grids. And so the second project I'm going to show is some forecasting here. This is just a bunch of notebooks that I built actually on a paper that I co-authored that's about sort of residential battery control. And so this is forecasting for energy prices and different energy demand. It's an incredibly interesting problem that is really blowing up with new AI models, etc., stuff like that. And so even though this is a bit hard to look at, I think a better sort of visual is to understand the models themselves and the sort of interesting things that you can do with these models. So a couple of the different model architectures that I've had that would have been in that Jupyter notebook are LSTM to FNN, so different model architectures that use different types of neural networks, obviously trying to do things like, one, capture temporal dependency, and then two, capture sort of different inputs like the amount of solar radiance for solar panels and stuff like that. Basic LSTMs, basic FNNs. I tried a CNN on top of an FNN and a CNN on top of an LSTM. You can also do stuff like gradient boosted regression to understand different factors in something like PV production and then feed that into an FNN or feed that into another regressor. And so there's some really interesting model architectures that you can have where you're using some of these tools in cool ways to understand energy prices as they come, and then you use those forecasts to actually optimize the control of the grid. Here, for example, is a web app. This is like just a basic overview, but here's a video of a web app that I built, both the front end and the back end, that does sort of this real-time optimization. This is in real time optimizing the energy prices, but it's also optimizing a battery, and it's sort of displaying that in the front end use. And so the third thing that I'm really interested in doing is turning this into a product. We have these really cool and technically difficult problems like forecasting, optimization, grid modeling, etc. But how do we make that actually usable for something like utility or grid user? Well, this is the project I want to continue in summer. This, for example, is a function that does something called stochastic optimization, so an advanced form of optimization under uncertainty. And I actually created sort of like this tree-like architecture to understand forecasts. But this is part of a helper package that helps with a Django project that I have that is trying to roll a lot of these products together into something that utilities and grid operators can use to make a more efficient and reliable grid with some of these advanced features. And so I know this moves really, really quick, but essentially it's a cool project for a couple reasons. One, it's exciting because there's a real impact to it. It has the ability to make grids more efficient, effective, and reliable, which has impacts here at home with data centers and abroad as the world develops. And then two, it's also an incredibly interesting question from a computation standpoint, everything from advanced optimization models to sort of cool AI model architectures. And so I would be super, super excited and thrilled to continue this project throughout the summer if I get YC funding. So thank you very much for the opportunity. I hope to hear back.